27.40. The plane of a 5 centimeter by 8 centimeter rectangular loop of wire is parallel to a 0.19 Tesla magnetic field. The loop carries a current of 6.2 amps. What torque acts on the loop? What is the magnetic moment of the loop? And what is the maximum torque that can be obtained with the same total length of wire carrying the same current in this magnetic field? So for part A, what torque is on the loop? So torque is given by mu cross B, where mu is our magnetic moment and mu is equal to I times our area vector. So our area vector, just like with Gauss's law, comes out perpendicular to the surface. So our torque we can write as IA cross B. So in this case, our A is coming out normal to the surface, and our B is going that way. So those two things are perpendicular. And when two things are perpendicular, their cross product just simplifies to multiplication. So IAB. So here our current is 6.2 amps. Our area is a rectangle, so length times width. So 0.5 meters times 0.08 meters. And B is 0.19 Tesla. So our torque, 6.2 times 0.05 times 0.08 times 0.19 gives us 0.0047. And the units of torque are newtons times meters. So we can find the direction that our thing is going to rotate. So when you have a torque, you get rotation, right? By using our right-hand rule. So let's look at this wire over here. So this wire over here has a current going this way. So this wire, because it's a current in a field, is going to feel force. According to IL cross B, my force is my thumb, is going to be going into the page. So it's going to be rotating this way. Whoop. So out of the page here, into the page there. Swoop, swoop. Alright, so for the next part, what is our magnetic moment? Well, hey, look, mu is just I times A. So mu, our magnetic moment, is I times A, which is 6.2 amps times 0.05 meters times 0.08 meters so it's 0.0248, and the units of that are amps times meters squared, so currents times areas. So this is a vector still, so this has a direction. So because we had our A coming out of the page initially, I'm going to say out of the page. Doesn't actually matter. Depends which side you're looking at it from. So that's the value of our magnetic moment. And then if you look at which way your forces are going, that's going to tell you your torque. So part C, what is the maximum torque that can be obtained with the same total length of wire carrying the same current in this magnetic field? So again, our torque is IAB. So we want to keep the current and the magnetic field the same. We want to keep the total length of wire the same. So the area that's going to maximize our, the shape that's going to maximize our area using the same amount of wire is going to be our circle. So that's going to be A times pi r squared times B. So if I know the circumference of my circle, that's the length of my wire, that's 5 plus 5 is 10, plus 8 is 18, plus 8 is 16, or 26. Wow, can't add today. So total length of wire is 26 centimeters. If I take that wire and I stretch it around in a circle, that's 2 pi r is equal to 26 centimeters. So r, 26 divided by 2 divided by pi is 4.14 centimeters. So the maximum torque that I could possibly get, if I just plug that in here, 6.2 amps times pi times r squared times b so the maximum times pi times 0.19 times 6.2. So maximum torque that I can get is 0.0063 newtons times meters. And that's by making a circle.